Slide 1. Peripheral circulation is a series of slide tape programs developed and produced by the American Physiological Society. This is Arterial and Venous Systems, Part 1. Content expert, Dr. Shu Chen, Professor of Physiology, Columbia University College of Physicians and Surgeons. 2. The first program in this series presented a discussion of hemodynamics. The programs that follow discuss exchange of materials between blood and tissue and the local and neural control of systemic circulatory function. Please note that a printed study guide accompanies this program. It contains the full program text and references for additional reading. 3. In hemodynamics, we discussed some basic principles of fluid flow and examined the factors responsible for dissipation of pressure in a simple fluid undergoing laminar flow through a rigid tube. As expressed by Poiseuille's law, the volumetric flow rate is equal to the product of the pressure drop, the viscous resistance factors, which are the fourth power of tube radius divided by fluid viscosity and tube length, and the constant pi/8. 4. We applied these principles to an analysis of the more complicated hemodynamics of blood flow, where a viscous, inhomogeneous fluid flows through distensible vessels with irregular geometry. We analyzed the factors contributing to both viscous and turbulent resistance, and we examined the likelihood of turbulent flow as described by the Reynolds number. 5. In this program, we discussed the arterial and venous systems, their organization and geometric features, the distribution of blood pressure, blood flow, and resistance to flow, the nature of vascular distension and capacitance, and finally, the forces acting on the vessel walls. 6. Your first objective is to be able to describe the architecture of the vascular system and the distribution of blood flow and blood volume within the system. 7. The sizes and numbers of vessels, blood flow rates, and blood volumes vary throughout the arterial venous system. Although these variables cannot be shown in scale, this schematic reflects the basic architecture of the vasculature. The arterial circulation is generated by repeated branchings, increasing the number of vessels in successive generations. On the venous side, the confluence of vessels results in a reduction in number. There are approximately the same number of veins as there are arteries. Anatomically, each artery is accompanied by a corresponding vein. 8. Because of the large range involved, many variables in the circulatory system are plotted on a logarithmic scale. This plot of the number of vessels in the systemic circulation indicates that the single aorta delivers blood to about 1 billion capillaries. On this and similar plots, the letters A, C, and V indicate the arterioles, capillaries, and venules, respectively. 9. The size of blood vessels varies greatly in the circulatory system. With branching in the arterial system, the radii of individual vessels in successive generations become progressively smaller. For example, the descending aorta has an average radius of approximately 1 centimeter. A small artery may have a radius of 1 millimeter. The smallest radii, approximately 2 to 4 microns, are found in the capillaries. As venules converge to form veins, their radii increase progressively. Notice that the radii of veins are larger than those of corresponding arteries. The ratio between the radii of corresponding veins and arteries is approximately 1.4 to 1. 10. The range of vessel radii is so great that they are also plotted on a logarithmic scale. Note again that veins have slightly larger radii than their corresponding arteries, and that the smallest radii are found in the capillaries. 11. Vessel size may also be compared in terms of cross-sectional area. The cross-sectional area of a cylindrical vessel is equal to pi times the square of its radius. Since the ratio of radii between corresponding veins and arteries is approximately 1.4 to 1, the ratio of their cross-sectional areas is approximately 2 to 1. 12. The total cross-sectional area of any generation of vessels equals the number of parallel vessels in the generation, n, times the average cross-sectional area of the individual vessels, pi r squared. In the arterial network, with successive branching, the increase in the number of vessels more than compensates for the decrease in the cross-sectional area of individual vessels. Therefore, there is a progressive increase in total cross-sectional area as one proceeds along the arterial network toward the capillaries. 13. As veins converge, the decrease in the number of vessels causes a progressive reduction in the total cross-sectional area, despite increases in the radii of individual vessels. 14. The total cross-sectional area in the systemic circulation reaches its highest value in the capillaries. Because of the extremely large number of capillaries, their total cross-sectional area is approximately 500 times that of the aorta. Since the total cross-sectional area of a single vein is approximately twice that of its corresponding artery, and since there are essentially the same number of arterial and venous vessels, the total cross-sectional area of veins is about twice as large as that of arteries. 15. The volume of a vessel is equal to the product of its cross-sectional area, A, and its length, L. Since arteries and veins have essentially the same length, and since the cross-sectional area of veins is approximately twice that of corresponding arteries, it follows that veins contain twice as much blood as arteries. 16. In fact, the arteries contain less than 30% of the total blood volume, the veins contain approximately 60%, and the capillaries contain no more than a few percent. The remainder of blood volume is contained in the chambers of the heart. 17. The capillaries have a large total cross-sectional area, but the short length of individual capillaries yields a very small total volume. If one takes the total cross-sectional area of the capillaries as 1,500 centimeters squared, and the average capillary length as 0.05 centimeters, the total capillary blood volume is 75 milliliters, which is only 1.5% of a total blood volume of 5 liters. 18. Next, we will consider the relation of blood flow to the vascular architecture. In a normal individual, the cardiac output from the left ventricle moves through successive segments of the circulation and returns to the right atrium. Therefore, in each generation of vessels, the total flow must be equal to the cardiac output. For example, if the blood flow at the root of the aorta equals 5 liters per minute, total blood flow through nearly 1 billion systemic capillaries and venous return to the right atrium also equal 5 liters per minute. 19. While the total flow through every generation is equal, the mean linear velocity of flow varies throughout the vascular system. This is because mean linear velocity is equal to total volumetric flow divided by the total cross-sectional area, and the total cross-sectional area changes markedly in the vascular network. As the total cross-sectional area increases progressively from the root of the aorta toward the capillaries, the mean linear velocity decreases from approximately 25 centimeters per second to about 0.05 centimeters per second. The mean linear velocity in the great veins is approximately 12 centimeters per second. 20. Since the mean linear velocity in each type of vessel varies inversely with the total cross-sectional area, the mean linear velocity plot is the inverse of the cross-sectional area plot. The capillaries have the slowest mean linear velocity, which favors the exchange of substances between capillary blood and tissue. Since the total cross-sectional area of veins is larger than that of corresponding arteries, the mean linear velocity in veins is slower than that in a corresponding generation of arteries. 21. 1. Rank order the arteries, capillaries, and veins. Use 1, 2, and 3 for the following variables: area, mean velocity, and volume. 2. Given cardiac output of 5.4 liters per minute, which is 90 cubic centimeters per second, and a mean capillary velocity of 0.05 centimeters per second, calculate the total cross-sectional area of all systemic capillaries. Please stop the tape while you answer these questions and those that follow throughout the program. Restart the tape to check your answers. 22. 1. Capillaries have the greatest cross-sectional area, followed by the veins and then the arteries. Since mean linear velocity is inversely related to the total cross-sectional area, the greatest mean linear velocity of blood flow is found in the arteries. It is slower in the veins and slowest in the capillaries. The veins contain the greatest blood volume, followed by the arteries. The capillaries contain a very small fraction of the total blood volume. 2. Total cross-sectional area of any vascular generation is equal to the total volumetric flow divided by the mean linear velocity of flow. In this case, the calculated total cross-sectional area of the capillaries is 1,800 centimeters squared. 23. Your next objective is to be able to describe the distribution of resistance to flow throughout the arterial and venous systems. 24. This schematic shows 5 generations of vessels connected in series. Each generation consists of a set of parallel vessels. In order to determine the distribution of resistance through the entire system, we must first understand how individual resistances can be combined when they are arranged in parallel and in series. 25. If we consider a single generation, the contribution of individual parallel vessels to the resistance of a generation can be analyzed. The total flow, Q, is partitioned into Q1 and Q2, flowing into the parallel branches. The total resistance, RT, is defined as the pressure drop, P1 minus P2, divided by the flow, Q. The individual resistances, R1 and R2, can be calculated by dividing their respective flows into the common pressure drop. Therefore, the total resistance and the individual parallel resistances all have the same pressure drop in the numerator, but different flows in the denominator. The point is that since Q1 and Q2 are each less than Q, the parallel resistances are individually greater than the total resistance. For the purpose of computation, parallel resistances are often written in terms of their reciprocals. In this way, it can be shown that the sum of the reciprocals of the individual resistances is equal to the reciprocal of the total resistance. 26. Applying this relation to a generation with 4 equal individual resistances, Ri, the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances, or 4 over Ri. Generalizing this relation further, total resistance in a generation of parallel vessels is equal to one of the individual resistances divided by the total number of such resistances in the generation, N. 27. The number of vessels in a generation is only one of the geometric factors determining its resistance to flow. In terms of Poiseuille's law, the resistance contributed by a single vessel is directly proportional to the vessel length and fluid viscosity, and is inversely proportional to the 4th power of the vessel radius. As we have just shown, In a generation of parallel vessels, the total resistance is also inversely proportional to the number of vessels in the generation, n. The combined effect of these geometric factors, including the constant 8 over pi, on flow resistance is referred to as vascular hindrance. The point to remember is that total resistance in a generation of parallel vessels is equal to vascular hindrance times fluid viscosity. 28. When generations of parallel vessels are arranged in series, each contributes a fraction of the total pressure drop. In this example, the total pressure drop, P1 minus P4, equals the sum of the individual pressure drops, P1 minus P2, P2 minus P3, and P3 minus P4. The total flow, Q, is the same through each generation. 29. The resistance contributed by each generation of vessels, R1, R2, and R3, is equal to the ratio of the pressure drop across that generation to the total flow through that generation. Since the total pressure drop equals the sum of the individual pressure drops, the total resistance in the series RT equals the ratio of the total pressure drop to the total flow. Therefore, the total resistance equals the sum of the individual resistances in the series. 30. A plot of the pressure drop along the length of the circulatory tree reflects the relative contribution of each vascular generation to total peripheral resistance. The plot indicates that the pressure drop in the arterioles is greater than that in any other generation. The arterioles are therefore referred to as the major resistance vessels. It should be noted that other parts of the circulation, especially the very small arteries, medarterioles, and capillaries, also contribute significantly to the total resistance. This diagram is a generalized pressure drop curve and applies to tissues such as the skeletal muscle and skin. 31. The total peripheral resistance in the systemic circulation can be partitioned into two serial elements, using the middle of the capillaries as the point of separation. All resistances upstream on the arterial side are considered the precapillary resistance, RA. It is equal to the difference between mean arterial pressure, PA, and mid-capillary pressure, PC, divided by the rate of blood flow, Q. All resistances downstream on the venous side are considered the post-capillary resistance, RV. It is equal to the difference between mid-capillary pressure, PC, and great vein or right atrial pressure, PV, divided by the rate of blood flow, Q. 32. In this example, we use the values of 92 millimeters mercury for mean arterial pressure, 17 millimeters mercury for mid-capillary pressure, 2 millimeters mercury for right atrial or great vein pressure, and 100 milliliters per second for total blood flow. We obtain a precapillary resistance, RA, of 0.75 and a postcapillary resistance, RV, of 0.15. These values are expressed in resistance units of millimeters mercury second per milliliter. 33. The total peripheral resistance in the systemic circulation can be calculated as the difference between mean arterial pressure and right atrial pressure divided by the total blood flow. The total resistance, 0.9 millimeters mercury second per milliliter, is the sum of the pre- and post-capillary resistances. 34. As shown in the previous slide, the total peripheral resistance, RT, equals the difference between mean arterial pressure, PA, and right atrial pressure, PV, divided by the total blood flow or cardiac output. When calculating the total peripheral resistance, the right atrial pressure may be neglected, since it is normally close to zero. This results in the simple statement that total peripheral resistance is approximately equal to the ratio of arterial pressure to cardiac output. Therefore, as an approximation, the arterial pressure is equal to the product of cardiac output and total peripheral resistance. 35. Sketch the pressure drop along the length of the circulatory system. Identify the location of the major resistance. 36. The pressure drops progressively along the path of flow in the circulatory system. The greatest pressure drop occurs in the arterioles, where the resistance is greatest. 37. Given these pressure values for the circulation through an organ, calculate the ratio of precapillary resistance to postcapillary resistance in the organ. 38. Precapillary resistance is equal to the ratio of the precapillary pressure drop of 72 millimeters mercury to the total volumetric flow. Postcapillary resistance is equal to the ratio of the postcapillary pressure drop of 12 millimeters mercury to the total volumetric flow. Therefore, the ratio of pre to postcapillary resistances is 6. 39. Your next objective is to be able to discuss vascular distensibility and define the determinants of vessel capacitance. 40. In our presentation of hemodynamics, we discussed the difference between intravascular pressures at two different points along the length of a vessel, P1 minus P2, which provides the driving force for blood flow. Since fluid pressure is exerted in all directions, however, it is also directed against the wall of the vessel. The difference between the intravascular pressure and extravascular pressure is referred to as the transmural pressure difference. It is this pressure difference that causes the distension of the vessel. 41. Since the extravascular pressure is generally small in comparison to the intravascular pressure, particularly for arteries, the transmural pressure difference is such that vessels are generally under distension. In fact, extravascular pressure is often so small that it may be assumed to be zero, and the numerical value of intravascular pressure in many cases can be taken as the transmural pressure difference. In this section, we discuss the effect of an increased intravascular pressure and consequent increases in vascular distension and intravascular volume. 42. A rise in transmural pressure causes increased vascular distension and an increase in intravascular volume. The vascular property that relates the transmural pressure and intravascular volume is called capacitance. Capacitance is defined as the change in intravascular volume per unit change in transmural pressure. It is dependent on the elastic properties of the vessel wall. 43. Capacitance is not constant at all transmural pressure levels. At low transmural pressures, a given change in pressure causes a relatively large change in volume. That is, capacitance is high at low pressures. At high transmural pressures, the same increment of pressure causes a smaller change in volume. That is, capacitance is low at high pressures. 44. The change in capacitance is caused by a change in the elastic behavior of the blood vessel wall as it is stretched. To understand how this happens, we must examine the various materials that make up the vessel wall. All vessels possess a single layer of endothelial cells lining their lumen. The endothelial cell layer and its basement membrane constitute the intima and are the only structural elements in the walls of capillaries. 45. In blood vessels larger than the capillaries, the intima is surrounded by a layer of media, which is usually bounded by an internal elastic membrane and an external elastic membrane. Within the media, there is vascular smooth muscle, separated into layers by sheets of elastin. The number of these layers increases in larger vessels. 50 or more layers may be found in the aorta. Both elastin and smooth muscle provide moderate resistance to stretch. There are also some collagen fibers in the media. 46. The media is surrounded by the adventitia. With regard to vessel mechanical properties, the most important component of the adventitia is connective tissue composed mainly of collagen, which acts as a supportive element of the wall. When the transmural pressure is low, the collagen fibers are coiled loosely and offer little resistance to stretch. With increases in transmural pressure, however, the collagen fibers become taut and strongly resist the vessel expansion. 47. The mechanical properties of the vessel wall are reflected in changes in the pressure-volume curve. After chemically removing the elastic tissue, the initial portion of the pressure-volume curve is altered. The capacitance at low pressure decreases, indicating that elastin is primarily responsible for the high capacitance behavior seen at low pressure. 48. If the collagen is removed by chemical treatment, the capacitance at high pressure increases, indicating that the collagen is primarily responsible for the low capacitance behavior seen at high pressure. 49. As a result of the combination of material properties, the aorta and the large arteries can serve their capacitative functions in the normal pressure range, and they can also withstand very high pressure without rupture. 50. The elastic property of resting vascular smooth muscle is between those of collagen and elastin. Its contribution is not clearly identified at either end of the overall pressure-volume curve. However, when vascular smooth muscle undergoes constriction, the vessel wall is stiffened, and the decrease in diameter is accompanied by a reduction in capacitance. 51. The pressure-volume relation depends on the relative amounts of elastin, collagen, and smooth muscle in the vessel wall. Proceeding from the aorta toward the small arteries and arterioles, the relative amounts of elastic fibers and collagen decrease progressively, while the relative amounts of smooth muscle increase. 52. On the venous side of the circulation, as the size of venules and veins becomes larger, the amounts of smooth muscle, elastin, and collagen increase. In comparison to arteries, the walls of the veins are thinner in relation to their radii. 53. A comparison of the pressure-volume curves of arteries and veins shows that the veins are more distensible. That is, they have a higher capacitance. The arteries are less distensible. That is, they have a lower capacitance. Since venous pressure is much lower than arterial pressure, the normal operating point on the venous pressure-volume curve lies in the high capacitance region. This graph shows that veins have a larger volume at lower pressure than arteries, and that the veins can undergo a greater change in volume for a given change in pressure. For these reasons, the veins are referred to as the major capacitance vessels. 54. With aging, the capacitance of the arterial tree decreases. This is because the elasticity of the connective tissue decreases, causing the arteries to become progressively stiffer. Furthermore, the arterial pressure increases with age, shifting the pressure-volume relation into the lower capacitance portion of the curve. Notice that the volume of the system is greater in old age due to the increase in vessel diameter. 55. Given this curve for a large artery in a young person, sketch the pressure-volume curve for a vessel with higher capacitance. For a given increase in transmural pressure, compare the increase in volume for each of these vessels. Finally, sketch and discuss the effects of aging on the capacitance of the artery given. 56. In the vessel with a higher capacitance, a given increase in pressure results in a larger increase in intravascular volume than the same pressure increase in a vessel with lower capacitance. With old age, the capacitance of arteries decreases. One reason for this is the deterioration of the more distensible elastic tissue in the arterial wall. Another reason is the increase in arterial pressure with age, which causes the pressure-volume relation to operate in the low capacitance portion of the curve. 57. Your last objective is to be able to describe the forces developed in a distended vessel wall, to discuss the balance of transmural pressure and wall tension, and to compare wall stresses in different parts of the vascular tree. 58. Recall that the transmural pressure difference, represented here by P, exerts the distending force on the vessel wall. 59. Distension of the vessel causes stretching of the wall and leads to the generation of circumferential tension, T, in the wall. Tension is the force per unit of vessel length measured in dynes per centimeter. 60. Consider the forces acting on a plane that bisects the vessel along its length. The force of the distending pressure, P, is balanced by the force of the circumferential wall tension, T, generated within the vessel wall. 61. Pressure is the force exerted per unit area. The total pressure force, Fp, acting on the plane, equals the product of the pressure and the area of the plane. This area equals the product of the vessel diameter, 2r, and vessel length, L. 62. The circumferential tension is the force per unit of vessel length. The circumferential force, Ft, in the wall, which opposes stretch, is given by the product of tension, T, and length, L. Since the circumferential force acts on both the top and bottom sections of the wall, the total circumferential force is 2TL. 63. At equilibrium, total tension force and total pressure force are equal. Therefore, the wall circumferential tension required to maintain an equilibrium radius equals the transmural pressure difference, P, times the radius, R. The equation relating circumferential tension, transmural pressure difference, and vessel radius is the Laplace law. 64. The Laplace law, as just stated, does not consider the role of wall thickness in generating tension. The wall tension actually is distributed over many layers, each of which contributes a fraction of the tension needed to offset the distending pressure. A further development of the Laplace relationship expresses circumferential stress, sigma, which has the unit of force per area, as the tension, T, per unit wall thickness, W. 65. The Laplace law can be rewritten to show that at equilibrium, the wall stress equals the product of the transmural pressure and the ratio of vessel radius to wall thickness. 66. It is interesting to compare wall tensions and stresses at different points in the vascular system. For example, the wall tension in the aorta is estimated to be 10,000 times that in the capillaries. But since the wall thickness in the aorta is about 1,000 times that in the capillaries, the circumferential stress is only on the order of 10-fold. Thus, although the capillary wall is subjected to less circumferential stress than the aorta, the difference is not as striking as would be indicated by considering the wall tension alone. 67. Since pressure, radius, and wall thickness vary considerably in various parts of the circulatory system, the circumferential stress also varies. Circumferential stress is highest in the aorta, where high pressure is accompanied by a relatively large radius to wall thickness ratio. Since the pressure and the radius to wall thickness ratio both decrease toward the arterioles, the circumferential stress decreases progressively. 68. On the venous side of the circulation, the progressive decrease in pressure is accompanied by an increase in the radius to thickness ratio, resulting in a relatively constant circumferential stress throughout the venous system. The circumferential stress is generally lower than that on the arterial side. 69. Consider now the effect of elevating transmural pressure. Since the arterial wall is incompressible, the volume of the wall remains constant. As an elevation of pressure tends to increase the radius, it also tends to make the wall thinner. The Laplace relation indicates that if the pressure were doubled, the circumferential stress required to balance the distending pressure would be more than twice its initial value. 70. Fortunately, the vessel wall becomes progressively stiffer when distended. This makes it possible to generate the passive circumferential stress needed to maintain the equilibrium at a larger radius in the face of an elevated pressure. 71. Otherwise, the increase in pressure with its attendant increase in the radius to thickness ratio would overwhelm the available circumferential stress and cause unlimited expansion of the radius, resulting in vessel rupture. This indeed happens in regions of aneurysm where the vessel wall is weakened. 72. Finally, we should mention that contraction of smooth muscle cells in the vessel wall, particularly in arterioles, causes an increase in circumferential stress, which tends to constrict the vessel. This is referred to as active circumferential stress. 73. Under this condition, the total circumferential stress, sigma T, is composed of an active component due to muscular contraction, sigma A, and to the passive component due to the distensibility characteristics of the vessel wall, sigma P. 74. Since the vessel wall becomes thicker as the radius becomes smaller, less passive circumferential stress is needed to balance the existing transmural pressure in the presence of active circumferential stress. 75. Sometimes in the arterioles, where very strong contraction of the smooth muscle may occur, the active stress generated may be so high that it exceeds the stress required to balance the existing pressure as the radius becomes progressively reduced. Under this condition, smooth muscle contraction may cause the near occlusion of the arteriole lumen, despite the presence of significant pressure upstream. 76. Write the Laplace law for circumferential stress in a cylindrical vessel. Include the units of measurement. Briefly compare circumferential stresses in the walls of arteries and capillaries. 77. The Laplace law states that circumferential stress in dynes per centimeter square equals the product of the transmural pressure difference in dynes per centimeter squared and the ratio of vessel radius in centimeters and vessel wall thickness in centimeters. The walls of arteries are subject to higher circumferential stress than the walls of capillaries. This is mainly because of higher arterial pressure. Although the capillaries have much smaller radii and thinner walls than arteries, the radius to thickness ratio does not differ dramatically between capillaries and arteries. 78. This concludes the first part of arterial and venous systems. We have discussed vascular organization and geometry, the distribution of blood pressure, blood flow, and resistance to flow, vascular distension and capacitance, and the forces acting on the vessel wall. To assess your understanding of these concepts and for a list of additional readings, please refer to the study guide that accompanies the program. 79. In the second part of this program, we discuss arterial systolic and diastolic pressures, the determinants of pulse pressure and mean arterial pressure, conduction of the arterial pressure pulse wave, and venous blood storage and return. 80. This program is part of the Peripheral Circulation Series. It was developed and produced by the American Physiological Society. Copyright 1981.